Welcome to Business Calculus, section 3.6 on related rates. This section builds on the previous section where we did implicit derivatives. This is a little bit harder. It's harder in the sense that all the variables typically depend on time. So for example, in our very first problem, we have y is x cubed plus 2. Now what's going on here, if we really write it all out, is y depends on time. X also depends on time. So it's not like we normally have where we have f of x. Here, both the x and the y depend on time. Alright, so it makes it easier if you write it this way so you don't forget. So we're going to want to differentiate all the way across, but in this case with respect to time. Alright, so the derivative of y with respect to t is dy dt. Next, I've got a derivative of a function raised to a power plus the derivative of the constant 2. Well, the derivative of the constant 2 is easy. That's just 0. And again, this was just dy dt. In this case, this is a chain rule. I'm differentiating a function raised to a power. So the power comes out in the front, same inside function. You decrease the exponent by 1, so 3 minus 1 is 2. But then, by the chain rule, it's times the derivative of the thing that was on the inside. So if we shorten this then, it looks like dy dt equals 3x squared multiplied by dx dt. At that point, you look to see what information was given, and what was given is dx dt is 2, that rate of change, and this is when x is 5. So at that point, you simply plug in the numbers and things are easy, and you get 150. Let me mention that all of the worked out examples for the homework are here at the beginning of the notes. At the end of the notes, you have 2 pages of exactly how the homework looks. Okay, so question 2. We have x squared plus y squared equals 13.05. Our goal, they would like us to figure out what is dx dt. Alright, so let's see. X of t squared, y of t squared, and the 13.05. We differentiate all the way across with respect to time. Again, the derivative of the constant is easy. That's just 0. Each of these is a chain rule. You have a function raised to a power. So the number goes in the front. So it's 2x, the thing on the inside. 2 minus 1 is 1, so these exponents are just 1. But by the chain rule, it's times the derivative of the thing on the inside. If you remember the way this was written previously, we had the derivative with respect to x of a function raised to a power. This was one version of the chain rule, and this is n. you take that function, subtract 1 on the exponent, but it's multiplied by the derivative of the function on the inside. And that's what's going on here. Alright, now since we wanted dx dt, I'm going to move all the y stuff to the right. I need to get dx dt alone, so I'm going to divide both sides by 2x. The 2's would cancel, and then I get minus y here over x times dy dt. Now, at that point, we go look to see what information we were given. We were given x is negative 2.7, y is 2.4, and dy dt is minus 2. Now, if we fill all that in, it looks like we can just calculate it, and you would end up with negative 1.777. The problem is MyMathLab is going to count that wrong. It wants it as a fraction. So how in the world do you make this thing into a fraction? Well, the trick is the following. You've got a minus over a minus, which makes it a plus. If you multiply top and bottom by 10, so 10 over 10 is really just 1, that would give you 24 over 27 times minus 2. At that point, you can take a 3 into the top 8 times, a 3 into the bottom 9 times the minus 2, and you get minus 16 ninths. And at that point, MyMathLab is happy. So again, the main trick was to multiply by 10 over 10 to get rid of these decimals. All right, in question 3, we have the relationship that x, y is 21. And they want us to find dy dt. All right, so first off, I divided both sides by x so that I can get y by itself. I now write it with the time dependence. I don't really want to use the quotient rule, so I rewrote x of t as x of t raised to the minus 1. Remember, something to the minus 1 is really just 1 over x. Alright, so then when I differentiate, we get the derivative of y with respect to t. The 21 just sits there. The minus 1 would come in the front, the function that was there before, and then minus 1 more makes it minus 2 times the derivative of the thing on the inside. Alright, so when we clean all this up, what do we have? I've got a 21 times a minus 1, so a minus 21. I've got this x to the minus 2, so 1 over x squared, and then dx dt. They gave us a point, which was 3, 7, which means x is 3, y is 7, and they gave us that dx dt is 3. So we fill all this material in. Didn't really need y was 9. There's no y's in it, but we still had it. And so simplifying, one of these 3's will cancel, and you get 21 over 3, and you get a minus 7. So what this means with the little minus is that the rate is decreasing. All right, in question 4, You're standing by a lake or a pond, and you take a rock or a marble or something or a coin, and you take it and you throw it into the water. As you throw this rock into the water, you'll notice that it makes ripples, and the ripples are moving outward. So if you looked at it, you would see a small circle, a bigger circle, a bigger circle as the ripple moves outward. Each one of these is a circle with a radius. And what we know about circles is that the area is pi r squared. But in our case, the areas, as you can see in my bad picture here, the areas are getting bigger. Well, they're getting bigger because the radius on each one of these is growing. And so my formula really depends upon time. So the rate of change of the area, dA dt, this is a chain rule, the 2 comes in the front, 2 pi, still have r on the inside, and then by the chain rule times the derivative of the function on the inside part. All right, so now we were given r is 18 feet. We were given that the radius is increasing at a rate of 4 feet every minute. And so we fill this in, 2 pi times 18 times 4, and I get 144 pi square feet per minute. It's square feet because it's a area. Now in this case, they were looking for a decimal answer rounded to 3 decimal places. So take 144 times pi, and to 3 decimal places I throw away the last 3 and get 452.389. All right, in question 5 and 6, we're looking at some business problems. We have a cost function. So here's my cost function. It is time dependent, so C of t, and my X, my production, is also time dependent. And so when I differentiate with respect to time, I get dC dt. The derivative of 90,000 is 0. And then 30 dx dt. And they gave us that x was 5,000 and dx dt was 600. And so if you fill all that in, you get that the rate of change of the cost is $18,000. All right, r they gave us looks like 300x minus x squared over 20. So writing it dependent on time, we see there's going to be a chain rule on the squared part. So dr dt is 300 dx dt minus, all right, the 2 comes down. I've got a 2 over 20, which reduces 2 into 2 once, 2 into 20 10 times. So that's where this part comes, times the derivative of the stuff on the inside. If you then fill in x being 5,000, dx dt is 600, what you see is that the revenue with respect to time is decreasing. All right, and then if you look at the profit, it's revenue minus cost. And so we know that derivatives go across minus, and so I can simply just take my two answers. So here's dr dt minus dc dt. All right, and so I get that the profit with respect to time looks like this. And if we fill this in, we see that it is decreasing at a rate of negative 138,000. My costs were increasing at that time. So that's not good. My costs are going up, my revenue is going down. All right, and then in our last problem, let's see. They were giving us something about sales. Okay, so writing it in terms of time. It depends upon time, and so does the x that's up in the exponent of e. So remember what we had previously. If we have the derivative of e raised to a function, it's going to be e to that function multiplied by the derivative of that function. All right, so ds dt is easy. I got the derivative of the 70,000. I then have the derivative of the 50,000 e part. Well, the derivative of the 70,000 is 0. That's nice. And then I've got this piece. So the derivative of this piece, 50,000 sits there, e to the function, but then I've got times the derivative of that exponent. I got this little piece here on the end. All right, so what happens? Well, let's see. We get all this same front part. The derivative of this, I get the number, and then dx dt. All right, the negative 0.004, so 3 zeros and a 4, times 50,000 is 20. All right, it's about as simple as we can get it, and now you would plug in the 2,500 and the 240 for dx dt. When you simplify this, the negative 0.000004 times 2,500, that part is just e to the minus 1. And e to the minus 1 times the 240 times the 20, and we get 1765.821. But they said rounded to the nearest dollar. So our sales are increasing at $1,766 per week. So again, you just have to keep reminding yourself all variables depend upon time and treat them as chain rules. On the last part of this is the original homework with the answers from MyMathLab. I hope this helped.